Hello everyone and welcome. In the last two tutorials, we built a solid foundations. First by understanding the core elements behind the small language models, then by exploring chat templates. And by now you have all the necessary tools to take a problem at hand and feed it into language models. But now we arrive at more important questions. What happens once we take these generalist models and apply them to real-world specialized problems? And this isn't hypothetical, this is the reality of today. Language models are already being used by subject matter experts to get help with highly specialized tasks. At a first glance, modern language models seem incredibly capable. Ask them almost anything, and within a second, you get a fluent, confident answers. And that is exactly the problems. They sound so convincing even when they are wrong. We call this phenomenon model hallucinations. In general tasks such as document summarization or email writing, that might not be a big deal. However, in safety critical domains like medicines, fluency is not enough. What you really need is precision and consistency. For tasks like this, you need models with deep domain understandings. However, before diving into how to teach the model that kind of deep expertise, a process which we call fine-tuning, this lab will show you in a hands-on manner what the gap between sounding knowledgeable and being knowledgeable actually looks like. You will see where a generalist language models break down on a specialized medical question and answering tasks, and why that failure is the strongest argument for fine-tuning. Then with this, let's get into it. In this lab, we are going to assess the performance of a generalist language model in highly specialized tasks. Specifically, we are going to use Llama model, the model that we used during Lab 1 and Lab 2, for medical question answering tasks. In this lab, you will learn about PubMed Q&A dataset. You will learn about how to design a chat template. You will learn also how to assess your model without any kind of fine-tunings. And in practice, you will see that how the model is hallucinating for answering the medical questions. It is also highly recommended to review Lab 1 and Lab 2 for getting a full picture of explanation that I will provide it here in this lab. So as a first step, let's learn about the dataset that we are going to use here. PubMed Q&A dataset is a scientific benchmark for answering medical questions. Specifically, the field that we are going to use here would be the medical question, which often the paper title, which is rephrased as a direct questions, and scientific context, which are extracted from different portion of literatures, including background, method, and results. And as a target value, what we are looking for is a long answer or final decisions. So the final decision is a human verified label, which is in yes, no, or maybe. And the long answer would be the abstract or conclusion or human written summary of the findings. So for visualization, you could see here that these are the type of a question that we could have here. So basically, is the breast best for children with a family history of atopy? And then there are a couple of contexts here. So the task that we have here would be the provide the questions and the corresponding context, and predict the long answer and or final decisions. So for visualization, I include the pipeline here. So we would have a research question context as the input, and then we need to bring into the format of a chat template and predict either yes or maybe. And in a separate task, we would be able to ask a model to make their own reasonings. And you can see here in terms of available data, we have 1,000 samples available in this data set, which you can see the imbalance between the different classes, which are divided to yes, no, and maybe. And it makes sense because they are coming from published works. So therefore, people are mainly tend to publish about their positive results. That's why you see, a lot of confirmed conclusions which lead to positive results that have been published. We have less data on no and least data in maybe, because basically people are not tend to publish about the result that are ambiguous, right? So for simplicity and complexity, I decided to drop the no class and being focused on yes and maybe, because during setting up this tutorial, I understood that these two classes are very hard to be distinguished. So in purpose, I wanted to make this work, this tutorial, a little bit more complex. However, we reduce the number of samples for simplicity, because we want to have also easy assessment on this task. The data set has been created, the subset has been created here, and I provided in the repository of the project. So you could see that we have 110 samples in yes class and 110 samples in in maybe class. So the first thing that we need to do, we need to check our environment to see that if everything is set up. So I have a torch available, I have a CUDA available. As I'm using PGX machine, I have a GPU GB10 available, and huge amount of VRAM for one local machine. However, for this lab, you do not really need to have such a big machine to be able to conduct that. You could simply use Google Colab with T4 GPU, similar to previous lab. If you're using Google Colab, you may move on and install these dependency on a slot and scikit-learn to be able to run this assignment, this lab. So the first thing, similar to two previous labs, we need to load our models here. Further explanation about, deep dive explanation has been provided in lab 1 on this part of the code. So we have a model here, we have a tokenizer. In order to be able to run to the next level, we set to maximum context window to 1024, because it can be a little bit, the context could be a little bit big. So therefore I keep it to a higher value, but you should know that it comes with a more consumption of your memory. So the next step, what we need to do is that we create, we bring our raw data PubMed Q&A dataset into the templates, chat template, I would say. So we have this raw data. We need to define the role. I explained about them in detail in lab 2. We define the role for system, user, and assistants. Then we bring it into a chat template, and this would be the training ready dataset. However, for this task, we are not going to do any kind of training. For simplicity and coherency between this lab and next lab, I create this part that our data would be training ready. But there is no training going on here. For system prompt, that would be the most interesting part. I would say we need to give a character to our models and set our expectation. We call it as a system prompt. You are a biomedical question answering assistant. You will be given a question and context from PubMed abstracts, answer with exactly one word, yes or maybe. So this would be the expectation that we have from our models. So we define the role, as I mentioned, system role. We introduce our system prompt, and then we will have the user, which would be the content that we give it as input to the models, and which would be the question together with the context. And we will have like assistant roles that basically what should be the given this system prompt and given this answer and context, what should be the final decision here. However, as I said, we are not going to do any kind of fine-tuning. So therefore, during inference, we do not use assistant command, because we expect that the model predict it without any kind of fine-tuning for us. So then we apply the chat template. Is important for this case. As we create that, we keep that false, because we already provide the information to the models, the assistant part. So that too would remain to false. So let's run it. And what we are doing here, we apply this chat template with these mapping functions into the to the whole samples that we have in our dataset. So you could see that the chat template is look like that. I explained it in lab 2. So here is a cutting knowledge that the model has been trained with, and here is a date that I download the models. So the system prompt here is here, the question is here, the context is here, and if you want to use it for training, then the final output should look like that. Again, I create training and validation. As I said, there is no training going on here, but for the sake of coherency between this lab and the other one, I wanted to have like a fair comparison. So we already do our experiment on a validation set. I know this is not the best practice. We need trained validation and test, but for the sake of a tutorial and simplicity, we only have 2 sets here. So and all the evaluation that we get here is on a validation set. In total, we would have, I believe, 220 samples in total. And for validation, we would have 44 samples, 22 samples from yes class and 22 samples for maybe class. So as the first part of our evaluation on our generalist models or base models, we would like to predict given the questions and the context on llama models, if the model is able to distinguish between yes or maybe. So the question that we're looking here is that does the model follow the instruction based on the system prompt that we provided to the models, is exactly coming with a yes or maybe as output, and does the model is doing better than the baseline. The baseline here, as we have 2 classes, it could be yes and no. So random guess could be 50%. So it would be our baseline value. So what we need to do here, we basically, before running on a whole bunch of validation set, this evaluation, let's see what exactly is happening here. So we have a system prompt, as we explained before, and we pick only 1 sample here, right? So we have only 1 sample, which is sample number 24 within my validation set. Then we define a system prompt as well as the user. We define the system role and the user role. And basically, as a system, we give a system prompt. As a user, we only give a question and context. We expect that the model would predict it for us. But the important element is happening here. We have a tokenizer. We need to keep it false. And at generation, as we are doing inference, it needs to be set to true, because it will be the signal to the model that it says that it is your turn. So as you can see here, the final decisions and the grand truth should be maybe, but the predicted final decision is yes. So the model is not able to predict it properly. But now let's set this add generation to false to see that what would be the problem here. As you can see here, the model does not understand that it is its turn to generate the output. So therefore, it basically reached to the assistant and said that, well, after that, they didn't ask me to generate any output. Therefore, it does not generate the output. And then again, we keep it to true. And you could see that it's able to predict the next token. So what we do, we get this prompt, we give it to the input, we tokenize it, we give it to the model, it generated, and then we do kind of post-processing to ensure that we only capture the output results. And at the end, we generate the prediction by doing kind of post-processing here. So now we run it on. We bring all this code that you could see here to a scale. So we define a kind of function here. We bring everything into these functions, and we let the model to run. First, initially on the only 6 samples, 3 from yes and 3 from, sorry, maybe class. And what you could see here as an output here is that the model is able to correctly predict the yes class. And I see some challenge on predicting maybe class. So that would not give me this kind of, good impressions about the output, because it sounds that the model is missing maybe classes. So let's run now on on the full validation set, which is 136. It takes some time maybe to get the kind of performance of the models. And as you can see here, the validation accuracy is basically 52%. It's very close to random guess. It means that 23 out of 44 of them are only predicted correctly, and then the rest it has been missed. So the random guess, if the always model predict one class, such as yes or maybe, would be 50%. But now you could see that is basically is not predicting properly. It's only 2%. Maybe it's based on chance. So now let's go and see which class is predicting more. And as you can see here, this is not a random guess. Is simply a systematic bias, because the random guess, it means that then you would be sometimes mixing between yes and maybe, but the model is not really mixing. It's always giving almost always giving kind of output on yes class, while completely ignoring the maybe class. So as you can see, we are like highly biased in a systematic way toward the yes class, and we are missing the other class. So basically, it suggests that the model is highly biased toward positive evidence. As we could see in terms of a data set, as I mentioned, the publicity available data sets, they are also prone toward a positive results. And as the model has been also trained on a publicity available data set, is always tend to give you maybe the positive response on the observation that it has within this task. So that was the observation that we had here. For next task, what we would like to do here is that we see that how we would be able to enforce the model now, given the questions and the context that we have here, to not generate the yes and no, but rather make a medical reasoning, give us more explanations. So this is very easy. What you need simply to do is that you just change a previous system prompt, and we simply ask to the model to answer with a comprehensive medical reasoning in a long format, right? We could also change it in one sentence, maybe. Maybe I could in one sentence. Let's see if it followed it. Follow my instruction. So as I said, everything remained the same. Nothing will change. Only system prompt will change. And let's see the output. So we have these questions, and basically it came with a kind of answer. So if you read that, you would be able to see that blind pedestrians were the least accurate, reliable in making a street crossing, etc., etc. And here is a grand truth. So if you read that, you will see that the model is writing in a quite convincing way that why the predicted result, they predicted yes instead of grand truth is maybe, and this is like a wrong predictions. We tested in a previous section of the lab. It's not included here, but I bring that result here, the prediction. So you could see that basically, although model is not predicting correctly, it provides you output which you can read it in a fluent way. It's quite convincing, and it's quite scientific. But however, the challenge is that is not right information. It's a misleading information, and this is quite dangerous for a case that the safety is important for us. So therefore, there is a huge gap between sounding knowledgeable and truly knowledgeable. So normally, if you read what doctor they write, they are not maybe writing in a very best grammatical correct way, but they convey their diagnosis in a proper way. However, here you can see that it's written in a perfect way, but the conclusion that we can get from a sentence is not, in reality, is not true. So therefore, we need to close this gap properly. And the conclusion here is that generalist models, although they seem to be convincing and they give us a kind of answer in a fluent way, in reality, the result that we get from them are misleading. And this is only a single example that I can show you here. You could also, after the lab, start to play around and see that how the model in reality is hallucinating. So we need to close that gap. At the end of the day, our conclusion here is that the model is a struggle with the biomedical decision making. So therefore, we need to close that gap, and that would be the fine-tuning, such that we need to train the model and basically tell to the model what kind of objective that we are looking for, and being able to enforce the model to learn about this domain expertise that we would like the model to learn to solve our problem. And also, as we can see, the model shows the class bias and unreliable prediction, which I believe strongly by this kind of fine-tuning approach, in this case supervised fine-tuning, we would be able to solve that problem. As an assignment, you could see that in this lab we use only either for let's go here, either we solve the problem for maybe class or for medical reasoning. So we treat these two tasks separately. You would be able for as assignment to ask the model to create both of them together. So that would be your assignment, that you ask a model to predict, to make a final prediction with medical reasoning. And I would be curious to see that how you would be able to do that. However, the mystery here, there is no change in code, but rather you should be focused on system prompt. That's the hint that you need to consider while you're working with this assignment. Thank you very much for your attention, and see you in the next lab on fine-tuning.